Hello everyone, in this video we will analyze gradient descent for convex quadratic problems and derive its oracle complexity. Before we start, let us briefly discuss the metrics that we have been and will use for specifying the oracle complexity. We were looking at the problem of minimizing f of x over x. The oracle complexity is usually specified as a value of t for which a certain quantity is below epsilon. The quantity or the metric depends on the problem. So far we have seen two metrics: the optimality gap given by fx minus fx star, which we used for the smooth and convex case, the gradient norm, which is used for the non-convex case. Over the course we will see another metric, which is the square distance from the optimum, that is norm of x minus x star square, which will also be useful in a number of settings, particularly when x star is unique and satisfies gradient f of x star equal to 0. We will continue to see other metrics as well when we start discussing constraint problems. At any point it will be important to be aware of what metrics are being used and if the bound on one implies that on the other. For this set of metrics we will relate them in different ways. So suppose that x star is the optimum and gradient of f at x star vanishes. Using this fact, we can write down the following properties. If f is L smooth, then we have that 1 by 2L gradient norm square is less than equal to the optimality gap, which is less than equal to L by 2 norm square of x minus x stars. While if f is mu strongly convex, then we have 1 by 2 mu subgradient norm square or gradient norm square greater than equal to optimality gap, which is greater than equal to mu by 2 x minus x star norm square. So gx is the subgradient of f at x. These inequalities are interesting because they relate the square norm of the gradient, the optimality gap, and the square distance from the optimum. We have seen all of these inequalities before, but I have simplified them by putting gradient of f of x star equal to 0. You can see that the sign of the inequalities is reversed when going from smooth to strongly convex. In fact, if a function is both smooth and strongly convex, then you can chain all of these together. So let us try to get some intuition for these inequalities. We consider a few scalar examples. First, consider an example of a function that is both smooth and strongly convex. So for this function, x star is equal to 0, and the first inequality says that the optimality gap does not grow faster than L by 2 norm of x minus x star square, which is evident from the fact that the dotted line is above the function. In other words, if we are able to derive an upper bound on the distance from the optimum, it follows immediately that for a smooth function, the optimality gap is also upper bounded. Since the function is strongly convex, there is a dotted line corresponding to the lower bound as well. So the upper and lower bounds are sandwiching the function in between. The upper bound prevents the function from rising sharply, while the lower bound prevents the function from increasing too slowly or being flat in any region. In both of these, the gradient norm square can be interpreted as dependent on the square of the magnitude of the slope of the function at x. For smooth functions, the first inequality says that if the optimality gap is small, then the gradient norm should also be small. For strongly convex, it is saying the converse, that is, if the gradient norm is small, then the optimality gap must also be small. Let us look at another example, that of absolute value of x plus x square. This function is clearly non-differentiable at x equal to 0. So you can see that the function changes sharply at x equal to 0, and there is no quadratic curve that we can plot which would upper bound it. But we can easily lower bound it with x square. So the subdifferential set of the function f at x equal to 0 is the interval minus 1 to 1. So non-zero subgradients are possible. Therefore, the subgradient norm is not upper bounded by the optimality gap. Next, let us take a look at a function that has a flat region around x equal to 0. So this is a scenario where x star is not unique. Such a function is smooth but not strongly convex. As you can see, we can upper bound it using the quadratic function. In fact, in that case, the gradient of the function as well as the optimality gap are both zero throughout this flat region and starts to increase only beyond that. However, we cannot lower bound it using any quadratic function because of this flat region where the function is zero, so the lower bound would also be zero. Likewise, the gradient norm throughout this flat region is zero. Next, let us consider the application of gradient descent on quadratic functions, where we will see that it generally performs much better than it was in the case of general smooth convex functions. Let us consider the general quadratic form given by half of x minus x naught transpose q times x minus x naught, where q is a positive definite matrix and the eigenvalues of q are in the range of lambda min and lambda max. Recall that for a matrix, the condition number is defined as kappa equal to lambda max by lambda min. We are mostly interested in cases where this condition number is much larger than 1. If we minimize the function over Rn, it is obvious that x star is equal to x naught. Also recall that b was the initial squared distance between x and optimal x star. We have the following result for constant step size gradient descent. For gradient descent applied to quadratic problems, the oracle complexity to ensure that the squared distance from the optimum is less than epsilon is given by order of kappa log b by epsilon for the choice eta equal to 2 divided by lambda min plus lambda max. Observe here that the oracle complexity is much better than what we obtained for the smooth convex case. In fact, it is at par with the iteration complexity of the bisection algorithm that we discussed earlier. This kind of dependence is called the linear convergence. If you look at the plot of the bound on the squared distance from the optimum against the number of iterations t while using the logarithmic y-axis, then it would be a straight line. The slope of the straight line depends on the condition number kappa. So if the condition number of q is large, then the number of iterations required to reach a certain accuracy would also be large. As you can see, it is much better than the 1 by epsilon rate, which is called the sublinear rate. The proof of the oracle complexity result is direct and just involves two steps. The first step, as before, involves establishing a one-step inequality. We can observe here that the gradient is given by q times x minus x naught. So the gradient descent update is written as xt plus 1 equal to xt minus eta q xt minus x naught. Now subtract x star from both sides and recall that x star is equal to x naught. So we have that xt plus 1 minus x star equal to xt minus x star plus eta q times xt minus x star. So the right hand side can be written as I minus eta q xt minus x star. Now take L2 norm square on both sides to get xt plus 1 minus x star norm square equal to I minus eta q xt minus x star whole norm square. So we can see that all we need to do is to bound the right hand side with respect to the norm of xt minus x star. For this purpose, recall the definition of the 2, 2 operator norm of the matrix Q, which is given by max over x not equal to 0, L2 norm of qx divided by L2 norm of x. This gives us the bound xt plus 1 minus x star norm square less than equal to L2 norm square of I minus eta q times L2 norm square of xt minus x star. This is a one-step inequality, but it is only meaningful if it is a contraction. That is, the distance of xt plus 1 from the optimum is less than the distance of xt from the optimum. So let us make sure that the one-step inequality is in fact a contraction bound. It would then guarantee that the iterates are coming closer and closer to the optimum at every iteration. Now generally, for any symmetric matrix A, the L2 norm of A is given by the eigenvalue with the largest magnitude. You can try to prove this by writing the definition and then carrying out eigenvalue decomposition of A. The eigenvalue of I minus eta q is given by 1 minus eta times the eigenvalue of q. So the eigenvalues of I minus eta q are between 1 minus eta lambda max and 1 minus eta lambda min. Both of these quantities could be positive or negative. So generally we have that the L2 norm square of I minus eta q is equal to the maximum of 1 minus eta lambda min square and 1 minus eta lambda max square. Substituting, we get xt plus 1 minus x star norm square less than equal to max of 1 minus eta lambda min square, 1 minus eta lambda max square times xt minus x star square. So this is the contraction bound. Now we just need to choose eta so that the bound is the most effective. In fact, we want to minimize this particular term max of 1 minus eta lambda min square, 1 minus eta lambda max square. Now if you try to plot this as a function of eta, we will see that this function is 1 when eta equal to 0, and then it decreases from there. But when eta is large, it starts increasing. In fact, you can convince yourself that this is minimized when both the terms that are within the maximum are equal. And that happens when eta takes the value 2 divided by lambda min plus lambda max. So substituting, we have the final bound that xt plus 1 minus x star square is less than equal to lambda max minus lambda min divided by lambda max plus lambda min whole square times xt minus x star square. So observe that this is what we wanted. This is in fact a contraction bound, since the distance from the optimum is decreasing by a factor at every iteration. We can recursively apply this bound so as to bound the right hand side as lambda max minus lambda min divided by lambda max plus lambda min whole raised to the power 2t times x1 minus x star norm square. And finally, from the definition of B, we have this term is bounded by lambda max minus lambda min divided by lambda max plus lambda min whole raised to the power 2t times B. In other words, we can see that the distance from the optimum decreases exponentially with the iterations t. Let us then get the required oracle complexity bound. Let me just write down the inequality that we have obtained so far, which is that xt plus 1 minus x star norm square is less than equal to lambda max minus lambda min divided by lambda max plus lambda min whole raised to the power 2t times b. That is, the square distance from the optimum is decaying exponentially with t. Equating the right hand side to epsilon, we can then calculate t as 1 by 2 log c times log of b by epsilon, where c is this ratio lambda max plus lambda min divided by lambda max minus lambda min. If you recall the condition number, which was kappa equal to lambda max by lambda min, c becomes kappa plus 1 divided by kappa minus 1, and it can be written as 1 plus 2 divided by kappa minus 1. So if kappa is much greater than 1, then log of c is approximately 2 by kappa. So substituting it back, we get our oracle complexity bound as order of kappa log b by epsilon. In summary, we have been able to show that the oracle complexity for solving quadratic problems is much better than the general convex problems that we have been earlier considering. So that is all for this video. In the next video, we will look towards generalizing linear convergence results and see other kinds of functions which also give us linear convergence rates.